Yo, what's up, calculus students? Uh, this is lesson one homework video on limits. Limits very much the building block of calculus because we're going to talk about things that are very, very close, like infinitely close. If you understand the concept of infinitely close, you'll better understand how we introduce our first major new concept of the derivative. So um, here's how we understand that concept through limits. What we challenge you to understand is like, do you understand what you're approaching, not necessarily what you have at a certain location? So, for example, and here's the situation we're giving you. We're either going to give you a graph, or later in the homework we give you just a function. I think during the lesson we gave you both. That way you could try to understand one versus the other. Many of you were good with the function, and then not really sure about the graph. But like maybe look back at your notes and see how they're connected. Um, what I like to say is that if we have this notation, this from the left notation, it just says a little bit less than one. It's almost like, hey, if you use x equals 0.99999, which I'll do in a second, this is a little bit less than one. Now think about like getting closer and closer to one. So maybe like starting, and we're going to look at our graph now, starting at 0.5. Okay, well, where you are, you're on this graph. You immediately look above or below, and you can see to the left of one, we have this kind of quadratic piece that we're going to pay attention to. But let's be more specific. Let's get close to one. Let's start at zero point 0.5. Okay, I'm here. Let's go to 0.75. Okay, I'm right here. Let's go to zero point 0.9. I'm right here. 0.99, 0.9999. You can see this graph is kind of telling you that this piece, which stops at 1, will be approaching this y value of 3. So I'm going to put my answer 3 here. However, if I went onto the other side to the right of one, you're thinking about using 1.001, but it might be easiest to start at like 1.5. You realize that at 1.5, you are using this piece. To the right of one, this is the piece that is defined. This is like when I gave you the function notation, I would have said, use some x squared plus something, something, something value for x's less than 1. Use this, I don't know, flipped square root something, something, something for x is bigger than 1. And use this point for x equals 1. So it's like to the left of 1, use this. To the right of 1, use this. Okay? So that's the idea that might help you if you're confused about this stuff. If I go to 1.25, I'm right here. If I go to 1.01, I'm right here. 1.001, I'm right here. 0001, I'm right here. I get closer and closer to where this open circle's location is, which is at 0. Now, since this does not equal this, you just answer this. Too many students, when asked the question, what is the limit without a plus or a minus? I call it the limit in general. Too many students think that this is a different question from these two, but this is combined with the previous two. You don't look at your graph when you're asked this limit as x approaches 1. You don't say, okay, let me look again. No. You just look at this value and this value. If they're not the same, the limit does not exist. If they are the same, that's your limit. Okay? Don't look at anything else. Just look at these values to answer this question. Now, here we can see that at x equals 1, we are supposed to be using this 0.2. Now, this is like why we would answer h of 1 is 2 here, because of this point at 1. We're not using this point, we're not using this point, we're using this 0.2. So this is what it would probably look like if I gave you the expression for it. Now, what about h of 0? Well, a lot of people get confused. They think to the left of 0, to the right of 0, we should be looking like to the left, to the right, we should be using this piece and this piece. But no, if I were to use a value that's just to the left of 0 or a value just to the right of 0, I'm really going to be in the same location. Now, make sure you understand these are x's. So a lot of people might be like looking over here, but this is not the right location. You should be looking right here at negative 0.001, right here at positive 0.001, and you could see both of those values are approaching, and we have that point there at 0, which is 1. So all of this is 1, this is 1. That means don't look at your graph, just look at these two answers. This is 1. And it just so happens that the point h of 0 is 1. Now, just so you know, this situation is what's typical. Typically, functions are just continuous. Maybe there's one little interesting thing, like one asymptote or something. But typically, functions are nice and they're smooth. Typically, limits and function values agree with each other. But to challenge you to make sure you understand the concept of a limit, we are going to mostly focus on the more interesting locations where things disagree with each other. Okay, so there it is. Now I'm just going to go for the graph. I'm not going to try to explain what the function would be in terms of expression. I'm just going to say, here's the graph. We're paying attention to 3 locations. We got -1, we got 2, and we got 3. So let's start with -1. To the left of -1, now don't make a mistake here. Less than -1 would be like negative 0.001. Greater than -1 would be like negative 0.9999. And again, think about adding more zeros, adding more nines. I'm going to pop over here. So it comes to, okay? And here is -1. This is exactly at -1. This is to the left. This is to the right. If I'm to the left of -1, I'm using this function. If I'm to the right of -1, I'm using this function. Okay? If I'm to the left, maybe this will help. Start at -1.5, then go to -1.9, then -1.999999. I can see I'm approaching 2. If I'm to the right, maybe I'm starting at 0.5, -0.5, then -0.75, then -0.9, then -0.999. We got to get really, really close to -1, but just a little bit bigger than. And I can see that my function values are down here, and they are getting closer and closer to this y location that is the point, -1. So I'm going to go ahead and just say at -1, I should be using this piece because of this closed circle. So I have this point -1. Now, don't look at your graph. You look at this value, and they don't agree, so the limit does not exist. Now, let's look at 2. If I'm to the left of 2, think about using values like that. Again, get closer and closer. We're talking about just like infinitely close, but to the left, infinitely close, but to the right, so less than or greater than. If I'm infinitely close to 2, but to the left of 2, I can see this is the function that I'm using to the left of 2 until I get to -1. This is the function that I'm using to the right of 2. And it goes on for forever and ever. So here's the idea. Start at like 1.5 here, 1.9, 1.999. I can see that I'm approaching the location of this open circle. So that's why the limit as x approaches 2 from the left, looking like here, is in fact this location of the open circle 1. If I'm to the right, same thing. Start at 2.5, 2.4, 2.3, 2.2, 2.1. These are the x's that I'm using to correspond with the y's. Remember, x's, y's for limits. The y value is approaching 1. Don't look at the graph to answer this question. Did you say 1 here? Did you say 1 here? That's your answer. Full stop. But we are being told that at 2, you should be using the y coordinate 3. Again, just as an example, we showed in class, like, what if you had x squared for x's not equal to -2, but use 8 for x equals 2. This is that example. It's like we want to use x squared everywhere except for at -2. This would be an example of the limit at -2 approaching 4. However, the function value at 2 would equal 8. Okay, that's like the whole with a point. What about at 3? Pay attention to not the y coordinate 3, but the x coordinate 3. So I'm to the right and I'm to the left of 3, and I can see I'm very close to the y coordinate 0 all the way around. And this is one of those typical situations. There's nothing interesting going on. It's boring, so that's easy. All right, another one. We got to the left of -2. To the right of -2, we got -1. We got 1. All right. I can see I got this piece, but I don't have a function value at -2. And then I switch to this piece at 1 to the right of 1. So x is bigger than 1. I'll be using that piece. I can see that I would use that piece at 1. I would not use this piece at 1, but I would use it for all values less than 1. So if I'm to the left of -2, -2.0001, okay, -2.001, come here, -2.001's right there. I can see I'm down here with this piece. I'm approaching this value. The value is -2. I'd be doing the same for the right. However, at -2, I do not have a defined function value. There is no equaling at -2. So this answer is -2. For -1, here is an x coordinate -1. Here is the x coordinate -1 to the left, to the right. We can see we're approaching 0. This is one of those boring locations where everything meets up. And now let's look at 1. To the right, to the left of 1 at 0.99999, to the right of 1 at 1.001. Here's 0.999 there. Here's 1.001. Let's start at 0.99999. Well, you can see that at like 0.5, I use the yellow piece. 0.9, I use the yellow piece. 0.999, I'm using the yellow piece. The yellow piece is getting closer and closer to the y value of -1. But to the right, I'm using like 1.5, I'm up here. 1.1, I'm up here. 1.01, 1.001. I'm approaching the y coordinate 2. It happens that at 1, I should be using this piece. I see this closed dot. That's kind of like that piecewise function that we looked at. X plus 3 is less than 1. X plus 5 is greater than or equal to 1. Like that whole equals to says like use this piece at 1. Don't use this piece for less than 1. So I do have this y coordinate 2. These align. However, to answer this question, look at this value, look at this value. They don't agree. Don't look at anything else. The answer does not exist. Okay. I feel like graphs sometimes are harder for students than the function expressions. So, like, if you were good with this in class, you're probably good for this on the homework. Maybe the graphs you'll need to practice and make sure you got right. Because I noticed students were good. They understand that this is x equals 1. Since it's x equals 1, I will be plugging it into this blue piece because 1 is greater than or equal to 1. Plug it into the blue piece, I get 0. Hooray. My cursor paused. Okay. One from the left. One from the left is like 0.999. Okay, 0.999 is a value that is less than 1. Since that's a value that's less than 1, I'm going to plug it in here. Now, here's what we tried to explain in class. If you plugged in 0.999 repeated into this, okay, you are going to essentially be plugging in 1 into this. The value you get when you plug in 0.9 repeated will be extremely close to the value you get when you plug in 1 into this. So don't plug in 0.999, rather like understand that you would plug in 0.999 just to the top. And when you do plug that in, it's like plugging in 1. When you plug in 1, you get -2. Hopefully we understand that. Here, 1 from the right, you're thinking about 1.001. That is a value that's bigger than or equal to 1, which means you should be thinking about using this piece for it. Well, if I plug in 1.001 into this, I'll get something extremely, infinitely close to what I would get if I plug in 1 into the bottom piece. If I plug in 1 into the bottom piece, I get 0. Don't care about anything that's going on. To answer this question, I will look here and here. They do not agree with each other. This limit does not exist. What about f of negative 2? Well, f of negative 2 is a value that's less than 1. So we should just plug it in here, and I should get negative 5. Hooray! What about negative 2 from the left? Well, that's still a value less than 1. I should still plug it in. Sorry. It's not negative 2. It's positive 2. What about 2 from the left? I give you these questions for a reason. 2 from the left, which is like 1.999. 1.999 is still bigger than 1. A lot of people just assume that this notation left means, oh, use the one on the top. No. It's like 2 from the left, 1.999 is still a value that's bigger than or equal to 1. You should be using the bottom piece. If you plugged in 1.999, you'd get a value extremely infinitely close to what you'd get if you just plugged in 2. Why don't we plug in 2? Because it's easy. That's 2 squared minus 2, which is 2. What about 0 from the right? I give you this for a reason because I want you to think, oh, I should be plugging in 0 into the bottom piece. But no, 0 from the right is like 0.001. That's a number that is less than 1. I should plug it into the top. When I plug it into the top, I get negative 3. What about 3? 3. Okay, well, let's think about 3. Now, I don't ask you for the one-sided limit, so you have to do it yourself. You got to think about 2.999. You got to think about 3.001. You got to find the limits for both of these. If they agree, that's your answer. If they disagree, then that's not your answer. So 2.999, still bigger than 1. I plug in essentially 3 to get that. I get 9 minus 3, which is 6. Okay, if I plug in 3.001, that's still a number bigger than 1. I'd still plug it into this. I'd still get the value 6. So yeah, I'm going to get 6 here. Okay? Good question. So this is like a function that jumps, which is why we have a limit that does not exist there. Let's check out this 3-piece function. And I give you 1, 2, 3, 4 locations. But again, to be able to answer these questions, since they don't have like a plus or minus, you got to do it yourself. You got to look at negative 1 from the left. You got to look at negative 1 from the right. Let's just kind of like figure out those values, and then I'll underline with colors so we can keep things coordinated. So negative 1 from the left is like negative 1.0001. That's going to be a number less than negative 1. So I'm going to denote that with red. Numbers less than negative 1. Okay, cool. If I did negative 1 from the right, then I'm talking about negative 0.9999. That is a number bigger than or equal to negative 1, but is also less than 2. So this actually falls into this interval where we are between negative 1, including negative 1, and 2. So I'll denote that with blue. Okay. So this number gets plugged into the blue. This number gets plugged into the red. Let's do that. If I plug in this number, I'll get something extremely similar to if I get, or like infinitely close to what I get if I plug in negative 1. When I plug in negative 1, I get 1. So that's the left-hand limit, 1. Let's go and plug in this number into the blue piece. If I plug this number into the blue piece, it's going to get a number infinitely close to if I plug in negative 1 into the blue piece. If I plug in negative 1 into the blue piece, I get 1. Since this and this are the same, guess what? We have a limit. That limit equals those numbers. What is going on, if you look at it graphically, is that this x squared piece would meet up with this 3x plus 4 piece, and that way we're approaching the same y value from the left and from the right. What about at 0? Well, you got to go 0 from the left and 0 from the right, but guess what, my friends? 0 from the left and 0 from the right both fall in between negative 1 and 2. So that means I'm just going to be plugging those two numbers in here, would result in 4 on the same, for the same 4 for both of them, and that must be my limit. This is my left-hand limit, this is my right-hand limit. There it is, 4. Let's check at 2. We got to go 2 from the left. I'm going to do 1.999. That is a number that is less than 2, so I'm going to use the blue piece. Let's all of a sudden look at 2 from the right. That's like 2.001. That is a number greater than or equal to 2. I need another color. Why don't we just go with this green? So I will be plugging that into x is bigger than or equal to 2. So that's this guy. If I plug this number into the blue guy, I would get something extremely close to 10. If I plug this number into the green guy, I'd get something extremely close to 9. So this is the left-hand limit. This is the right-hand limit. Therefore, in general, the limit as x approaches 2 does not exist. This number is different from that number. I should be using the limit notation, but I'm just kind of like, I'm being a little bit lazy here. And that's fine. I'll do it for the last one. Hey, on a free response question, when we take the AP test and when we start practicing, this is more important for like checking continuity because that's a question that you may have. If they ask you to find a limit, you must show limit notation in both directions, and you must show that the left-hand limit equals the right-hand limit. And that is what needs to be shown with correct limit notation. If you do not do that, and if you just do what I just did, you might not get credit. So this would be, and probably can't see me because of my face, this is necessary for proper free response notation. If I plugged in 2.999 or 3.001, they are both bigger than 2. So I'm going to plug in those values into the green piece. If I plug in essentially 3 into the green piece, I get 8 on both sides, whether you plug in 2.999 or 3.001, they're both close to 3, so you plug both into there, and you get it. Cool. All right, here's that point. It's like I'm going to use 3 minus x squared for everywhere, except for at 2. So let's practice limit notation. So this is like for free response. I ask you, what is the limit as x approaches 2? It's really a question that we're going to have to be like, is the function continuous at 2? You must show the limit as x approaches 2 from the left of the function. 2 from the left is like 1.999. 1.999 does not equal 2. Okay, so since it does not equal 2, I'm going to plug it in there. I get 3 minus essentially 2 squared, which is 3 minus 4, which is negative 1. If I then go to the other side and I go 2 from the right, I'm plugging in 2.001. That does not equal 2. Therefore, I would use this piece. Plugging in 2.001 will give you something infinitely close to what you would get if you plug 2 in here. So I get negative 1 as well. Since the left-hand limit and the right-hand limit equal negative 1, I get negative 1. However, at 2, I get 7. Okay? This is like a hole with a point. This is very much a good question where you have to practice understanding a table of values, and that table of values produces a limit statement that you need to write. Well, I'll start with f of 2. What's going on right at 2? F of 2 is undefined. There's no point there. But if you said as we get closer to 2, but from the left, and I use 1.999, this function f of x seems to be getting closer and closer to 11. Cool. If I go and look to the right of 2 and I use 2.001 and more zeros, infinitely amount of zeros, I can see I'm getting close to 11. Therefore, my limit equals 11, even though I don't have a function value. Again, you don't care about the function value when you're answering limit questions. This is how you are tested about understanding limits. What about f of 5 here? There is no function value here. F of 5 is undefined. Now let's look here to the left of 5 using 4.999 repeated. I'm getting closer and closer. Don't say the answer is 5.999. Don't say it's 5.999. Think about continuing to add nines, and you would continue to add nines here. So like if I continue to add nines and nines, and I'm getting closer to 5 for my x's, and I'm getting closer to 6 for my y's. Limits are about approaching. So I'm approaching this whole number 6. Infinitely close. If I go to the right side and I go to the right of 5, this is g of x. Here's to the right of 5, I'm getting closer and closer to the y value -1. Since this value and this value disagree with each other, I don't care about this. I don't care what's going on at f of 5. My answer is does not exist for the general limit. Function values are defined or undefined. Limits exist or do not exist. Now, what about these expressions where it's not piecewise? It's just like, here's the limit, and I'm just going to give you the function, like this is f of x. Well, just remember, typically, functions are boring. Here's x squared minus 1. What's going on? Nothing fancy. There are no holes, there's no jumps, there's no asymptotes. Everything connects. Well, guess what? All of our function values will have limits that are equal to the function value. So if I have a point, I have a limit at that point. So like typically function values and limits agree with each other. So if I ask you what's the limit as x approaches 2 of x squared minus 1, you just need to pop over to 2. You need to figure out what this point is. Maybe don't even think about plugging in 1.9999 and 2.001 because you're like, well, I'm just going to plug those values into this, and you will get values infinitely close to the function value. You should just think about plugging in 2. Typically, function values and limits agree with each other. So for all of these, your first step should be like, can you plug in the value? And do you get something? Yes. Make sure you know the cosine of 0 is 1. If you're making a mistake on that, then that's a problem. I give you that for a reason because everybody messes up on cosine 0. Sine of 3 pi over 2, -1. Okay. Secant of pi over 6. Let's do this in our head. Cosine of pi over 6 is the root 3 over 2. Flip it. It would be -2 over root 3. Oh, I don't know why I said negative. Positive 2 over root 3, which is 2 root 3 over 3. Oh, what about e to the x? I don't know what to do. It's like just plug in pi and you get e to the pi. Like e to the x is continuous. E to the x doesn't have any fancy things going on with it. Like e to the x is essentially boring. It's important, but it's boring. So like, bam, plug in pi. You get e to the pi, whatever that value is. Don't use a calculator, just leave it like that. If I'm just to the left of pi or just to the right of pi, I'm going to be just infinitely close to e to the pi. This is a good challenge for you. Let's see if you can get this right. What happens when you plug in 4 into that? What happens if you plug in -4 into that? Yeah, it's like a lot of people will get the same answer, but this order of operations, since there's no parentheses, means square the number first, then take the opposite of it, or then multiply by -1. Exponents come before multiplication. If I take 4 and plug this in, I get -16. However, if I take -4 and plug it in for x, I'd get +16. So let's not make those mistakes. This deals with the jump function, and I gave you a lot of these. Don't know why I gave you lots. It's a function that you need to be familiar with. We did it in one of the classes. We didn't do it in the other. But let's see what's happening. And this is kind of what I did for when we have holes. If I plug in 2.999, okay. 2.999 minus 3 is going to be a number close to 0, okay? And that number close to 0, we are going to take the absolute value of and give me a positive number close to 0. Now I'm going to write it as a number, but it's a number very close to 0. Meanwhile, if I plug it in the denominator, I would get a negative number close to 0. Now here's the key. These numbers are the same. What happens if you divide something by itself? You get a negative answer. That's why I should get -1 here. Not a negative answer. If you divide something by itself, you get 1. If you have something divided by itself and negative, you get -1. The idea with this is like if you have x minus 3 over x minus 3 and just like cancel, you get 1. But if the bottom was negative, you get -1. That's why this is called the jump function. We jump from -1 to 1. If I plug in 3.001, it's the same thing. I get a number close to 0 that stays positive. I have a positive number close to 0. These are going to be the same numbers that are close to 0. They aren't 0, though. They are close to 0, which is why I get +1. This does not equal this, which means this does not exist. But I'm going to add a question here. What is f of 3? What is f of 3? If you plug in 3, what do you get? Oh, do you get 1? Do you get -1? You don't get anything. You're not allowed to plug in this number 3 because you get 0 over 0. 0 over 0 is undefined. You are never allowed to divide by 0, even if you have 0 over 0. Okay? So in this situation, the graph looks like the following. At 3, we don't have a point. However, we're approaching /on -1 everywhere to the left of 3 and +1 to the right of 3. Like this one, I'm trying to trick you, but hopefully you won't get tricked. If you plug in 5, you get +1. If you plug in 5, you get +1. Whether or not you plug in 4.999 or 5.001, you're still going to produce the same thing, which is a +2 on the bottom and a +2 on the bottom. So it'll be a positive over a positive always because we're to the right of 3. So this is 1. Hopefully you didn't get tricked. Let's look at this guy. Same deal, only there's one more thing going on. And this is going to help us when we get down here. If I plug in -0.001, I'm going to get 2 times a negative number very close to 0, absolute value, over a negative number close to 0. This turns into 2 times that number that's now positive close to 0, and this number that's negative close to 0. These numbers close to 0 are the same. When you divide something by itself, they cancel. What happens? We are left with the -2 as our answer. Do you see what's going on here? I don't like to say this is 0.001. I like to say it's a number and these numbers are the same. Now, when we go to this bottom one, this is where it's going to be like important for you guys to really pay attention. If I do it with a positive 0.001, 2 times a positive number over the positive number that's the same, since these numbers are the same, it will cancel. We'll get +2. This does not exist. Okay. It has to be the same to cancel because watch this, and this is the most important one. These are the ones that the students mess up on the most. They're thinking about plugging in 2.999 into x squared minus 9 over x minus 3. And they're like, okay, when I plug in 2.9999 and I square it and I subtract 9, I'm going to get a number close to 0. And then if I plug in 2.99 and subtract 3, I'm going to get a number close to 0. And then they cancel this and they say, okay, this has to be 1. But here's the key. This is not the same as this. They are different. That means if you plug in this in here and that in there, you do not get the same. You can't cancel those. You can't say it's 1. You can't say it's infinity. You can't say it's 0. But don't say this limit doesn't exist. A lot of people are like, oh, therefore it does not exist. Because if I do plug in 3, I do get 0 over 0. And 0 over 0 is bad, so my answer does not exist. Wrong. Instead, we have to somehow algebraically reveal what we would get when we plugged in 2.99999. And the way we can do that is by always looking to factor so that we can get that number close to 0 divided by that number close to 0 to cancel. Now, I don't want to cancel the x minus 3's, but I'm going to think about if you plugged in 3 or something close to 3, you are going to get 6 times a number close to 0. It's not 0. Over a number close to 0, that's not 0. And these numbers close to 0 will cancel. You do that on the right, you do that on the left, you get the same thing. Now, if I asked you what is, if this is like f of x, if I asked you what is f of 3, what would you say? Undefined. There's no function value at 3. However, we are approaching 6. This is the reasoning why holes are holes, because you will be approaching a value. You will essentially be using x plus 3 everywhere except for at 3, where you don't have a function value. Okay, so it's the same thing here. We want to plug in 0, but you won't get the same thing if you plug in 0.001 into these as those. So you can't just say it's 0 over 0. A number over a number that cancels and is 1. We have to somehow reveal the values we would get when we plugged in like 0.001 or negative 0.001. And the way we do that is by factoring. Here I'm going to factor out a greatest common factor. Oops. Okay. Now, when I plug in something close to 0, this number and this number, since we're multiplying, will give us numbers close to 0 times the stuff on the right. These numbers will cancel. Now, we got this number close to 0 plus 3, and we got this number 5 plus some number close to 0. Think about what happens when you plug in something close to 0. You'd get like a number close to 0 plus 3, and then 5 plus a number close to 0. These don't cancel and give you ones. You're not allowed to cancel over addition. You can cancel over multiplication, and there's the multiplication that allows me to cancel this. So you don't like cancel and turn them to ones. Instead, you're like, what's 3 plus essentially 0? 3. What's 5 plus essentially 0? 5. And that's why if you plug in 0 to the left and 0 to the right, you get 3/5. However, again, if I asked you what is f of 0, you would say it's undefined because you'd get 0 over 0. This is the idea behind limits. Same thing here. We want to plug in 2.99. We want to plug in 3.001. The only way we can do this is if we factor. Okay. And now let's think about this. If I plug in a number close to 3, this number and this number will be the same. They'll be close to 0, but the same number, this number close to 3 minus 1, whether you're using 3.001 or 2.999, will be a number close to 2. Great. Just making sure everything's good. These numbers will cancel, but they leave ones. Don't say the answer is 2. The answer is a half. Again, f of 3 is undefined, but we would be approaching this value 1/2. This is the idea behind holes and finding the locations. I hope you get that. The last one is a little bit of a trick, and don't worry about it for the quiz. This is something we'll kind of investigate further for next class. This does not exist because we don't get 0 over 0. When we get 0 over 0, like we want to be able to cancel those zeros, but we can only cancel those zeros when we have all the other information provided that like leaves us with something valuable, whether it's this or that. What we find is that when you get -2 over 0 or a number over 0, you have a vertical asymptote. Vertical asymptotes don't have limits. Don't worry about this quiz. Don't worry about this question for your quiz. Worry about everything else. Okay. I'd love to give you more practice. If you have some, come in before school. We can talk about it. Okay. All right. Hope this video works. The first time I recorded this homework video, it did not. So wish us luck. Peace.